Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah wassalatu wassalamu ala Rasulillah amma ba'du. Alhamdulillah, in this morning we can continue our lesson, and today we will finish our discussion about segment 3. After that we can discussing another material, and after we discuss the material about segment 3, what will what we will discuss next? I think in the previous meeting, or sorry. Yes, before segment 3, before we discussing about segment 3, we were discussing about probability, and then we still not discussing about graph theory, right? So I think after that I will try to explain about graph theory. All right. Before we start our discussion, let's pray together. Allahumma inna nas'aluka ilman nafi'an wa rizqan thayyiban wa amalan mutaqabbala. Rabbana zidna ilma warzuqna fahma. Rabbi israh li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Amin. After that, Rabbi already solved problem K. And then how about problem L? Alright, that's great. Abdullah Isbak already got accepted as well. And I think I haven't show you how to implement problem K. Then let me show you the general solution in general way. So this is the solution of problem L, right? This is the solution of problem L. Oh, no, I think here. After that, about problem K, after we create a persistent segment tree, we have to make the solution like this. Which one? Let me remove this first. Initially, we input all the variable and k and also array of a. Initially, we can build the initial version 3 and then we can build it. From that, we can input a variable a, and then we have to store a vector store of p, let's say, with size the maximum of a, because a never not greater than 100,000. So we can create an array of vector with size 100,000. Sorry, 100,000. So every time we input a, so we will push the index to vector a. So we push I to VA. After that, if the size of VA greater than K, so we have to remove the first barrier, right? So we have to remove the index of VA dot size minus K. For example, like this, we already has size S, for example. I think minus K minus 1. If this is equal to K, so we still not need to remove this. But after the size become K plus 1, we have to remove the first index or index 0. So we shall put minus 1 here. All right. And we will create any version. That's why we need persistent segment tree. And after that, we will input some query starting from the number of query, and then we will input x, x and y, and then we will change L and R here, or we can directly make it L and R, but we have to change into this formula. x plus mod n, or L plus modulo n plus 1. Alright, and then we also have to do this for R. Then if L greater than R, so we have to swap them. And then we want to do query starting from L until R. So plus will be equal to the version of R version. Okay, thank you. It is Q. And then we have to query starting from L until R. All right, then we have to output plus. Okay, this is the main function. How about the segment tree? Initially, the value is 1, right? All of the leaf value is 1. And we don't need lazy, right? We don't need any lazy propagation, so just ignore it. And then we want to do some query. So just leave it in this way. And then we want to do point update. Which is the update means changing into 0, right? Changing into 0. All right. Nothing changed except this. Okay, then just try to input the sample. All right, because the maximum of Q equal to the maximum of A for this problem. 26133. All right, I think there is a different value here. This is 3 plus 2 plus 1, 6. Do you see any mistakes? So let me debug version R. because k equal to 2, then when we try to query all of them, we already update for n1, right? So why this is still 6? I think I have to check about the index that already removed from the segment tree. And 3 and 4, 6. All right. Okay, I forget about this. When we update the value, then we have to save the pointer, right? All right, 2, 4, 1, 3, 2. This is the solution. And the main function is relatively short, but in order to do persistent segmentary, we have to implement this. Okay. Do you have any question about this problem? Open that. Let's move to the last problem. Here are some radio, and we have to create a dynamic segmentary, right? So we can try to copy from the template. Or let's just put by ourselves, since it is not too different. For the range update, we can just make it void, and then we turn it in this. After that, for this problem, I think there is no range update, right? We only do point update, so just remove this. Let's change it into void, and then we will make it y. After that, we can push both of them. Sorry, push and then update both of them. and then we will change the value and we don't need the return. And for this problem, we need some roots. We need maximum f root. So we have to create 10,000 segment trees. And then we need some query. And then how about the push function? We don't need lazy propagation, right? But we need to create the child. If the child is not exist, then we have to create it. We have to move it here and then just remove it. The value initially is 0. All right, this is dynamic segment tree. After that, we will input n and k, and then we have to build all of the road starting from 1 until 10,000, and then we will build a new segment tree, a new dynamic segment tree from 1 until maximum x, like this. Okay, after that we have to input x, r, and f. Sorry, I think we have to input them in pair or in struct, since we have to sort them. We have to sort based on the value of r. If the value of r is same, so we don't care whether which one is came first. All right, so we have to create a pair, and then a triple. And then you want to create an array of triple, which the size is n. And then we need n and k. So we will input R as the first, X as the second first, F as the second. After that, we want to sort them, and then we will do them starting from the last index, since we need to do starting from the larger R. Right. Then for each node, we will try to query from the frequency minus k. So it means this minus k until the frequency plus k, since the value of k is small. And don't forget to max it with 1, so it will never less than 1, and minus it with n, since sorry, with max f. Max f will be equal to this. And then there is also max x, right? 10 to the power of 9. This max f. And after that, we have to query. We have to store the answer. Answer plus by the query in root j. Root j dot query starting from x minus r. X minus r until x plus r. X means this. After that, we have to update. We have to update this. Sorry. We have to update in the root of the f, and then we will change the index of x become 1. All right. Or not always become 1, but plus 1. Or actually, because no two radius will share a coordinate, so both of them is correct. All right. After that, we can just output the answer. Okay, let's try to input all of the samples. Let value. Okay, this is just value, right? No need to use red here. All right, I forgot to define the first and second. Sorry, this is not R but A. Or sorry, the I is equal to AI dot first. Return red. Which one return red? Okay, here. Return it, return anything. All right, one. Two. And then also two. And finally, this is five. All right. Again, the main function is so short that we have to implement the dynamic segment tree. Okay. For this problem, is there any question? Okay. Then I think you have understood about segment tree and also the lazy segment tree. And persistent segment tree. Is there any question about all of them? All right. I think you already understood about them. So just try to solve the rest of the problem. Problem J until M. Then after that we will try to discuss about graph theory. Or is there any other suggestion about the material? Or you also can ask me some problem. So you can throw the link of the problem and then we can discuss it together. All right. Is there any suggestion? All right. You agree about discussing about graph theory. So until how far you already studying about graph theory. Do you know the terminology about graph? The graph actually some entities or some data that is connected with some relation. All right, then what we will say about this entity? What is the terminology that you already know? Not all right. Is there any other terminology? No, still about the entity, not the relation. H means the relation, right? And not means the entity. All right, that's great. The node or sometimes it called vertex or in the plural way we can call it vertex. All right, this is just the same meaning. Sometimes we call it node, sometimes we call it vertex. After that, the graph has some property or some types. There is a, all right, you already know. For example, directed, undirected, and then connected and disconnected, cyclic and acyclic, and what else? Weighted and unweighted. So about weighted, what does it mean? A weighted graph. All right, the edge or its edge, they has some weight. But sometimes weighted means weighted in edge and sometimes weighted in node as well, or both of them. And usually the graph problem is about a story problem, right? We will read the story. After that, we can represent the story become a graph. And then sometimes for each relation, there is a data attached in this relation. So we call it weight. But sometimes the weight is on the node. For example, there are some cities connected by roads and each road has length. So we can put weight here. And then sometimes, for example, each city has some capacity of people, for example. So we can put weight in the node as well. All right. And then after that, we need to know about graph representation. So how to store graph information in computer. So for human, we can inform the graph by drawing the diagram. But how about computer? How to start them? Of course, you already know how to do it. Can you mention about the way to represent the graph? How computer storing the graph? Of course, computer doesn't draw the diagram, right? So how computer store the information of a graph? Using what? Adjacency list. All right. And that's the most powerful one. And we usually use this. But sometimes we also use the adjacency matrix, right? And in the format input or input format, we usually use list, right? So just input array X and Y, and then we can conclude the graph. And sometimes we just input parent list for tree. Okay. And then, all right, I think we have to discuss about tree as well. What is a tree? Can you explain what is the definition of tree? Okay, acyclic graph, connected acyclic graph. Okay, we have to also say about connected, because if doesn't connect, so what we call it, acyclic disconnected graph. What is the terminology? We will call it forest, right? So this is also paradox, right? If we have a tree and we cut the tree, it become forest, right? So when we cut the tree, it become forest. This is the paradox. And then sometimes we define like this. Tree means connected acyclic graph, right? This is acyclic. But sometimes when we say about graph, means the cyclic one. Even acyclic graph also called graph, right? But because um, tree is more frequently appear in the problems, so sometimes we differentiate them. All right, and then the algorithm to solve them is also different, right? About the acyclic graph and cyclic graph. Actually, acyclic graph divide into two. It is tree and also directed acyclic graph. We usually use dynamic programming to solve dynamic acyclic graph and usually do the first search for tree. And about graph, there are some algorithm to solve it. All right. And do you know about JFS and BFS? Okay. And about disjoint set, you already know. All right. I think all of the basic you already know. I think I will, after that, I will just create the contest about basic graph to just solve them easily. And then how about shortest path? All right, about the properties. We can use GFS to get the properties of tree based on the problem. For example, the solution of the problem need the depth of the tree, for example. Then we can just find the depth using GFS, or for example, the height using GFS. Sometimes need pre-order or post-order, we can use GFS. So do you know about the height and the depth of tree? All right. Can you implement how to find the depth? I think I want to check your implementation about GFS. I will give you some tasks. For Aqua, please implement how to find the depth. And then for Hashim, please implement how to find the height. And for Hayan, implement about GFS in tree to find the tree properties. Implement how to find the size of subtree. And then for Rafiullah, please implement how to find pre-order. And then for Suhaib, please implement JFS to find what else? Depth, height, size. What else? I think that's enough. So just implement the skeleton of GFS. All right, if you don't know, uh, just implement GFS or the skeleton of GFS, and we will discuss it later. or for Suhaib, maybe we want to know the parent. So we do GFS to find the parent, right? Yes, this is the router tree. If this is not router tree, but we will do GFS from specific node, right? Usually we use first node if the graph is not rooted. All right. Sorry, I have to go to the toilet for a while. So just continue your implementation. Okay, let's discuss one by one. All right. I prefer to use this for TFS in tree. We can put two parameter and we don't need to use array of boolean. All right. And then we can just continue when in order to avoid visiting the parent, right? And then depth of the child equal to depth of the parent plus one. All right. This is also correct. We also can put the formula here. It is also correct. And about the height, height means the maximum height of the children plus 1. All right, this is also correct. And about this, is it 0 or 1? This is based on the problem or based on the preference. And then about the subtree size, equal to the sum of all the children plus 1. All right. Okay, that's great. And then about how to find the parent, we can just storing the parent each time we do GFS. All right, and then what is pre-order? Pre-order is usually used when we do some query and update in subtree. Have you seen the problem that we need to do query update in specific subtree? For example, a subtree that rooted in specific node. Have you encountering that problem, that type of problem? Right. Anyone ever see that kind of problem? Ever or even or not yet? Didn't solve, but ever see the problem, right? Sorry. The problem which we have to do query and update in subtree. For example, given a tree, a rooted in the first node, for example, and then for each query, we need to find, for example, the sum of all the value in the subtree. And then sometimes we need to update, which is we want to change the value of a specific node. Or for example, we will change all of the value in the specific subtree become plus 1, for example. Okay, then how to solve it? We can use segment tree here. And how to use segment tree if this is not an array but a tree, right? If this is a tree, then we can do like this. We can just find the pre-order. Pre-order means the starting time or the visited time. So, Let's say we have an integer time here. Time initially equal to 0. And then the order of this node equal to time. All right. So the value of root will be 1, and then for the child will be 2, and then will be 3, and so on. And then the sibling will be 6, and the children will be 7, and so on. We can make the order like this. Then this 9, 10, for example, this 11, and 12, and then 13, 14, 15, 16, and so on. All right. This is pre-order. Pre-order means we want to sort the node based on the time we visit the node. All right. You got it? Is it understood? Okay. Then how to use segment tree after we know the order? So we can store the value of this node in index 1 in segment tree, and then this node in index 2 in the segment tree, and so on. So if we see the graph here, the order here, every time we access the subtree, we always get the continuous index, right? Starting from t until 10, for example. For this subtree, starting from 14 until 17, and so on. So we can store the starting time, and then that's correct. We need to store starting time and ending time. So if we want to do query in subtree, subtree in specific node, for example, subtree below node x. So we can query starting from stx until nx, right? And the same way we can do it for update. Okay. Is there any question about this? You can find the material about pre-order, pre-order traversal. Okay. So is there any link to the problem? Sometimes in sometimes appear in Port Force problem, and the tag is just TLS and similar and data structure. So we'll try to find from the text TLS and similar, and also data structure. We can sort it from the easiest one. And then just take a random problem. And then let's read this. I think we use different trick for this problem. Here we know that for each node x, for example, we can jump until ax, sorry, below ground level, so x minus ax. Jump down, cannot jump down, okay. And then after jumping, then will be sleep exactly px. So after some node can slip into the other node, and we will reach the specific node. All right, so we can draw the graph based on the array P. For example, here the node 1, from the node 1 we can slip into the node 10, right? And from the second node we also can slip to the node 10. And then for the third node we also slip here. Maybe we can start from the last node, right? For 10 we will not slip at all, and 9 also. 8 will be equal to 10, sorry, okay, 8 will be equal to 10, and then 7 also, and then 6 also, and 5 also, and 4 just slip into 5, and then 9, sorry, 3 to 1, 3 to 1 also go to the 10. Then we will check from which node we can go up to ground level. From this we cannot, and we cannot also here. We cannot. For this we can. We can jump from the 5 meter below the ground and jump 5 meter. Alright. And this is all cannot. This also cannot. So the only option to go up is just go to the fifth node, right? And then how to go there? How to go there? We have to go to the four node, right? Yes, we have to go to the fourth node and then flip to this and then jump to the ground. All right. Then how to jump to the node 4? Then we can jump from 9, right? Jump from 9 and actually from 10 to 9 and then from 9 to 4. Okay. Then what shall we do next? I think we have to start how many number of jump we have to go to specific node, right? In order to find it, for example, the node 4, how many jump we have to do in order to go to the node 4. So in order to go there, we have to know for each children, right? For each children, how many jump to go there, and then after that slip to the node 4. And how to know this? How to know how many, or yes, how many node can go there? We can do 2 pointer, I think. Or can we use sort of pet here? Okay, I think we can do this way. We want to create a node from 1 until n. And then after that, we want to create another node that pointed to node that the frog will slip into the other node. For example, from 1 we will slip into 10, right? From 2 also slip into 10, and so on. And then after that, for each node, actually we can, what can we say? Can go to this and then this and so on until AX, right? But if we do that naively, so the number of edge will be quadratic, right? Or n squared. So how to optimize that? We can do a trick just like a segment tree. We can create a node that pointed to this and this with edge with weight 0, for example, or of them 0. And then we create another node that covering two nodes and so on. Okay, so for example, if node 5 can jump from 2 until 5, we can just make it pointing this and pointing this and pointing this. So this covering 2 and this is covering 3 and 4. And this also only covering 5. All right, so the number of edges will be equal to log n, just like the complexity of update in segment tree, right? All right, do you got the idea? So we use the trick in segment tree here. So how about the implementation? So when we input the array A and array B, initially we want to build a segment tree, just like a segment tree from when until n. And we will define the node like this. The original node starting from 1 until n, or from 0. And then the, or this is where we sleep at. And then from n plus 1 until to n is the original position. And then from 2n plus 1 and so on, this is the just like segment tree, segment optimization. After that, how to build the segment tree here. We just need to input this for the segment tree. So 2n plus x is children 2n plus 2x, and also 2n plus 2x plus 1. Alright, is the children. So we will build starting from 2n plus x. Or we can do like this. For example, this is the index and this is L and R. And then if L equal to R, then just return, sorry, if L equal to R, so we have to point the node, or yes, just point the node like this, the adjacent of 2n plus id, push back L. Okay, I think starting from 0, since we can jump until 0. And then for the other node, we will create an adjacency list like this. And then we have to build the children. Okay, after we build all of them, every time we input A, we have to, let's say this is update from node I. We want to, I can access from I minus A until I, right? Since it can jump until A. Okay, so update means like this. If x greater than R or y less than L, we can just return. But if x less than or equal to L and R less than or equal to Y, then we can make it like this. Adjacent of n plus y pushback ig. All right, it covering all the segment in ig. Open that. Don't forget to update each of them. Okay. Okay, I forget about one thing. Since we need to do shortest path, so we need index as well. Sorry, we need wake as well. The wake is just 0 for this case. There is no cost here. And also for here. I think the cost is here. When we go to the real node. After that, every time we input G, it means from the node G, the frog will sleep until the node I plus B, right? After that, we can do shortest path starting from the node 2n, go to 0 node. Okay. Do you know how to implement the shortest path? Not yet. Okay. Do you know about the Dijkstra algorithm? Okay, if not yet, I can show you the implementation directly. We want for the Dijkstra algorithm, we want to find the distance between the starting node or the source node to the other node. Can we do it Q as well? No. For Q, we use PFS using Q, and for Dijkstra, we need to use priority queue. So what is the difference? For PFS, actually we can also use PFS to find the shortest path, right? Since it is can traverse one by one starting from the source and then spread into the nearest, the nearest neighbor and so on. We can find the shortest path using PFS if the graph is unweighted. Okay, but what if the graph is weighted? Do you know how to find if the graph is weighted? That's it. We cannot do using Q because sometimes like this. For example, starting from this node, the weight is for example the weight is 1, and then this is the weight is 5, and then here the weight is 2, and here the weight is 5, and here the weight is 3, and so on. For example, this is 10. Yes, we need priority queue. That's it. So actually the idea is just the same as PFS, but we cannot do that since there is a weight here. So we need to do PFS, but starting from the nearest one. So we will visiting this at first before this, and then we also visit this before this as well, since the distance is just 3. After that, we will visit this before this, since this is 6. So we will visit it using this way. So the distance is 6, not 9. So the distance of this node is 16. Alright. So if the curve is unweighted, so we have to to use priority queue. Okay. But for this problem, actually we can avoid Dijkstra since the weight is actually just 1, but we need to combine between PFS and DFS, or we can do PFS like this. Let's use PFS starting from node what? Starting from node 2n. The distance is just 0, but we will use the queue here. Let's create a JQ. Do you know about JQ? Not priority queue, but JQ. Okay, what is JQ compared to queue and stack? Okay, we can push and pop from both sides, back and front. While queue, we only can push from one side. While the queue not empty, we will do PFS. the PFS is like this. We will do starting from what? Starting from the front, right? After that, we will pop front, and then we will iterate all the adjacent, right? The adjacent of now. For this case, the adjacent is the adjacency list using pair. That is the node and the weight. Actually, we can use a here as well. And then we need a distance. And I think we need backtrack as well, since we need to output the path, right? So we will the distance here and also the backtrack. And we can use array of distance to check whether it is visited or not. So I think we can start the distance starting from 1. So if the distance is not 0, it means already visited. But if equal to 0, then it is not visited yet. So we can visit this distance next dot 3 become the distance of now plus next dot second. Is if the cost is 1, then the distance increasing by 1. But if the distance is 0, we don't need to increase this. And then we will push to the queue, right? But we have to check first whether this is 1 or 0. If this is 1, then we have to push back since we will visit it later. But if this is 0, we have to visit this directly. So push front. Do you know this fact? For PFS implementation, we will use queue. If we change it into stack, it becomes DFS. Do you know about this fact? Just try to implement PFS and then change the queue become stack. Then it will become DFS. But usually if we want to implement DFS, we use recursion, right? But actually, we can also implement GFS using stack. Okay. And also about this, if we push back, so it means just like we do PFS, if push front, it means just like we do DFS, because we will do the not do the traversal one by one, but we directly visit until the bottom and so on. Why we do this? Because we want to do it directly. So for example, we have the queue here. For example, the distance in the queue is like this. This is 3, 3, 3, 4, 4, 4, 4, 4, 4. When we want to traverse starting from this node, if the distance become 4, then we will push it here. But if the distance is still 3, we will push here. Okay, you got it? Because some edge is weight 0. Okay, that's great. So we can differentiate them between pushback and push front. After that, we can output the distance of node 0 and -1 because we start from 1. Okay, and don't forget to use backtrack here in order to go there. We can visit now. Okay, let's try to input the sample. Okay, sorry, I have to remove this first. And then the maximum n is equal to 300,000. Sorry, I think this is not just max n, but 6 times max n. Since this is a segment 3 and then 2n. Okay, -1, sorry. So let me check the graph. or in order to check the idea, the TFS idea, let me just make it like this. We do brute force first before we optimize it. Starting from n plus I to j till -1. Okay, let's see. 0 to 2. So this is can go up 0, and then this is 2. This is also 2. And then 1, 1, 0. From this flip into this. Okay, I think this is n plus I plus A. Okay. N plus I plus A. So from 1 become 5, right? And then from 2 become 6, and 3 become 6 as well. This is 1. Okay, correct. After that, let's try the other symbol. This -1, okay. And the last sample, -1, yeah, unfortunately. Let's try to repeat this. I think this is starting from I, right? Okay, 3. After that, we want to output the backtrack. So let me create a vector. We will do backtrack starting from node 0. Till reach node 2 times n, right? Then we will go to the node, the previous node. Okay, after that, we will push back to the path if now is between n plus 1 and less than 2n. This is the original node. After that, we have to reverse the vector since we do backtrack and the path is reversed. So that we can just output the path. Okay, let's try to output this. Okay, sorry. Push back now minus n. 10, 9, 5. Sorry, I think not the original node, but the node before we sleep. So we don't need to minus n here. 9, 4, and also 0. Okay, we have to push 0 as well. All right, 9, 4, 0. Let's try to input this. When 0. Okay, I think the PF's idea is correct. Okay, is there any question about this? Okay, and then we have to optimize this using just like segment 3, right? We want to push, we want to visit this, but we have to, we don't want to do for loop like this. we have to make it more optimized. So in update, I think this is 2 times n, right? 2 times n push back, sorry, n plus y push back to n times it, to n plus it. Okay, let's do this. Okay, correct. How about this? Also correct. Okay. And how about this? Okay, -1. Okay, I think this solution is enough. Okay, for output the -1, we have to stop it directly. If this 0 equal to 0, it is cannot visit it. We cannot visit it, so just return 0. So we will avoid the runtime error. Okay, all right, this is correct, I think. I will try to submit it later. Then what is the complexity? The number of nodes is 6 times 3 310,000, so become around 2 million. Okay, and then the number of edges will be equal to this times log. I don't think so. I think n times logarithmic. For example, times 20. So become around 6 million because we use DFS or PFS, extended PFS. So the complexity is just ON. If we use Dijkstra, so the complexity will be n logarithmic n. So it will be around almost 1 second, I think. But maybe still accepted. Okay. All right. I think that's all for our discussion today. Thank you very much for the discussion. Mm. And see you later in Friday, inshallah. So let's close our meeting with praying. Allahumma anfa'na bima 'allamtana wa 'allimna ma yanfa'una wa zidna ilma. Subhanakallahumma wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Wassalamualaikum ala nabiyyina Muhammadin walhamdulillahirabbil alamin. Wassalamualaikum warahmatullahi wabarakatuh. Okay, sorry, is there any mistakes? Do you have any question? Okay, you have holiday on Friday. Okay, so see you later on Monday, right? Okay, thank you for the information and have fun in your holiday.